Good evening, everyone, and welcome to the Amateur Radio General Class, session number 14. During our previous session, we had a look at the sunspot cycle. We talked about the SFI, or solar flux index. Then we went on to discuss band propagation as it relates to the solar cycle as well as the sun's rotation. We discussed what a sudden ionic disturbance are. We also discussed coronal holes and coronal mass ejections. Then we discussed what are geomagnetic storms. Then we talked about the K index and A index. Then we also discussed maximum usable frequency, or MUF, and lowest usable frequency, or LUF. Then we talked a bit about automated receiving stations. Then we discussed propagation as it relates to short path and long path, as well as echo. Then we discussed atmospheric noise and static and its causes. And then we ended the theory with the ionospheric regions F2, E, and D. And then we did our usual question pool review. So our agenda for this evening: technical topics. We'll be discussing critical angle, critical frequency. Then we'll discuss what is the skip zone. We'll talk about scatter propagation, and then NVIS. And then we move on to the next topic, major topic, by going to notch filters, attenuators. We'll discuss what is the noise blanker function, also noise reduction. We talk about CW, or Morse code operations. We'll then discuss functions of the radio such as split operations and dual VFO. Then we'll talk about automatic level controlled, ALC. Also, we'll begin discussing linear amplifiers, and we'll talk about tube amplifiers. Then we'll touch on antenna tuners. Then we'll go to some instruments such as the multimeter, voltmeter, and so on, and also the oscilloscope. We'll discuss the antenna analyzer. We'll talk about what the two-tone test is, and then we'll end the theory by discussing what are bypass capacitors and ferrite chokes. So just a note for persons who are joining this session via YouTube and seeing this for the first time, we are currently performing the general class course. That's level 2 in the courses to become an amateur radio operator or licensed ham. And there's a level 1 course called the technician class. So we're at the general class, but there's a technician class course which was run several months ago. And on your screen is a link to the course. It's available on demand, all of the documents, as well as the playlist. So these are for your consumption as required, and also persons who would like a reminder or to review any of the technician class material. Okay. So in our general class syllabus, this is where we are in the curriculum. We are progressing quite nicely. We will actually wrap up radio wave propagation and begin amateur radio practices this evening. And we're making good progress, folks. We just have a couple more topics to go before we come to the end. So a reminder also, it's never too early to take practice exams. The practice exams available on these websites are using the same question pool that you will get in the actual exam. So feel free to avail yourselves of the practice exams. Very good evening to you there, Adish. Okay. This is a slide on anyone who would like to interact with React, the organization. There's a Zello channel. It will also help you begin learning about radio operating practices in a sandbox. It's not actual RF or radio frequency. And you can apply what you have learned using Zello. So anyone interested, you can have a look at the slide when you get the slide deck if you haven't seen it before. So this is an important slide for all of us that are participating in this course, the general class level, level 2. All of the material that have been distributed from the start of the course, as well as those that are delivered on a weekly basis, mainly the slide deck, are available at this link, gdocs.ttreact.com. Notice this link, there's no S in HTTP, right? So it's HTTP, not HTTPS. This is just a redirect link, and it will take you to cloud storage. So please be sure not to insert the S for this redirect link. And also the playlist as well of all of the videos are available at gvids.ttreact.com. You can, Friday evening is not the most convenient time for some persons, so you won't miss out because all of the recordings, once they stick, are available at this link. Right? And so far, we have been able to record all of the sessions thus far in the main. So please utilize these resources. We will not be emailing out attachments anymore because it fills up mailboxes quite easily, several megs per file. So no need to email. What we email are the links to the files as well as the videos. So you can utilize this at your leisure. Okay, just a reminder of the text that we're using. We're using the No Nonsense General Class License Study Guide, and highly recommended that you purchase the book, as well as there are other highly recommended texts from the ARL, for example, as well as Gordon West. Really good material. Avail yourselves as many as you can. We encourage you to support the authors. It's good for you to have these books as reference material. However, it's not absolutely required. You do not have to buy anything at all, but we are just recommending that you avail yourselves of the text if you're in a position to do so. And these are all available at Amazon or the author's website. We had no outstanding questions from last session. Right, so just a reminder what we are talking about. We are wrapping up discussions here, and we have a couple more slides. So we are talking about HF propagations in the main, and we are trying to, as a ham radio operator on one part of the earth, we are trying to communicate with our good friend, another amateur radio operator, on another part of the earth, and we're using our signals that's going to bounce or reflect or refract off of the ionosphere. That's the layer in the sky that contains those ionized particles that radio waves will bend in when it gets to that level. And there are different layers, as we saw last class. So this is what we're actually trying to do. We are not using terrestrial fiber optics or cell towers as ham radio operators. In this instance here, we're able to communicate wide area across the globe, thousands of kilometers or thousands of miles away, using our radio signals. So this is what we are trying to do. So we have a ground wave that will go up to a point, but then we have a sky wave that will go up into the sky and hit or reach the ionosphere. And some will pass through, but what we are trying to do is know and understand what will cause our signal, at what frequency, what sort of antenna we need to use, where do we need to direct our signal to be able to reach where we would like to. So we have a couple more slides talking about that. So we come to the concept of critical angle, and this is an exam question. What is the critical angle? So we need to be aware that when we send our signal up, and we talked about NVIS, and we'll also be discussing about NVIS again this evening, that when we try to send our signal up into the sky, to the ionosphere, that's called the angle of radiation, right? We are sending it, and we can do things, create our antenna in such a way, construct it in a particular way that will cause the signal to leave the antenna at a high angle of radiation like this, or at a low angle of radiation like this, or even lower angle of radiation like this. And you'll see when we send a signal at these low angles, the signal will certainly go further away, right? So this is as a ham what we are trying to do. We're trying to utilize the ionosphere. But we need to be aware of the concept of critical angle. And what the critical angle is, it is actually, we have it here as a definition. It says the critical angle, when referring to radio wave propagation, is the highest takeoff angle that will return a radio wave to Earth under specific ionospheric conditions. So let's dissect what this means. Critical angle. So that's the angle or the takeoff angle. We have a high takeoff angle like this, and then we have a low takeoff angle like this. So what we're saying is that the critical angle is the highest angle that will cause the signal to come back to it. Because if we go higher than that critical angle, it will go straight into space or outer space. It will not come back onto the surface of the Earth. So that critical angle is what we need to be aware of when we're trying to shoot our signal up into the sky. If we go too far off, meaning that the angle is higher than it should be for that particular frequency, then we will not be able to communicate. So we need to be aware of what that critical angle is. When we construct our antennas, we're using our antennas, we're using the particular frequency, we need to be aware of that. So also we have a little note here that frequencies greater than the critical angle are too steep therefore will not be refracted and instead will pass right through the ionosphere. So that's just a point here. So the critical angle is an important concept, and this is in fact an exam question, and hopefully these diagrams will help us understand what the critical angle is. And notice also we talk about the ground wave, and we also have something called the skip zone that we'll be talking about very shortly. So apart from the critical angle, we talked a bit about the critical frequency. So what is the critical frequency? So let's just read the definition here, and it's an exam question also. The critical frequency, when referring to radio wave propagation, is the highest frequency which is refracted back to Earth at a given incident angle. So for the particular angle, that highest frequency, so if we're in the HF part of the spectrum, if it's 28 megahertz or 14 megahertz, if that's the critical frequency, that's the highest frequency that will allow our signal to refract back to it. So notice all of these signals here are being refracted back, all of these here. But notice these are in fact going, into space. It's not being refracted back. So critical angle, critical frequency, two important concepts that we need to be aware of, and their exam questions. All right, so we just mentioned this concept of the skip zone. So let's take a moment to understand what the skip zone is. So we did say that if we have a transmitter on the surface of the Earth and we're trying to communicate with a ham across the globe, somewhere maybe hundreds and thousands of kilometers away, or hundreds or thousands of miles away, we are trying to use our HF frequency and we're trying to bounce it off of the ionosphere. We're trying to refract our signal and it will drop somewhere here. But notice when the angle of radiation that goes, right, it's leaving our antenna and going to the ionosphere and dropping far away. We have two signals that leaves our antenna. One is the ground wave, and our radio signal will happily hug the Earth and go to a certain point. But beyond that line of sight or that ground wave coverage, the rest of the coverage will be via the sky wave that goes up into the sky, bounces off the ionosphere. But there's a void or there's a gap, and that gap is called the skip zone. And that skip zone is an area that you will not have any communications because it is beyond the ground wave from your antenna, and it is before your signal drops back to the Earth via the sky wave or via the ionosphere, refracting your signal. So this is called the skip zone, sometimes called the dead zone. There's no communication there. But of course, we can as hams find a way to communicate, right? But just be aware of the definition of what the skip zone is. And here it is on your screen. The skip zone is the region where a radio transmission cannot usually be received via the ground wave or the sky wave. And we put here this red arrow to show you this range here. If a ham is on the surface of the Earth at this point, they will not hear, they will not receive our signals because it's dropping short or it's going over their heads. That's the skip zone or the dead zone. And it occurs between the point where the ground wave can no longer be heard, that's here, and where the sky wave first returns to Earth. So that's what we need to know about the skip zone. And hopefully this diagram here illustrates it diagrammatically. Okay, so even though we said that, we cannot usually communicate in the skip zone, let's talk about some concepts. As we discuss it, you'll see how maybe we can in fact have some communication. So we need to talk about the concept of scatter propagation. All right, so let's read out what scatter propagation is on your screen. So in scatter propagation, a small amount of the transmission is reflected back in the direction of the transmitting station, and the signal is heard in the transmitting station's skip zone. So we just said, the ground wave wouldn't reach, and the sky wave goes overhead, right? And therefore you have a dead zone or a skip zone. But there's something called scatter propagation or backscatter that will cause a little bit of the signal when it bounces onto this Earth surface. There's a scatter that goes back, and it could actually arrive in that skip zone or that dead zone that would otherwise not hear that transmission. But there are a couple things about that scatter or backscatter signal. First of all, it's very weak, or it's usually quite weak. It's because only a small amount of that signal is actually coming back via that scatter propagation, right? So while we would not normally be able to communicate, we can with a bit of a stretch, right? So that is called scatter propagation, and it's backscattering part of your signal into the skip zone that would otherwise not normally hear your signal. right? But there are some characteristics about that signal. You probably would have guessed it already. If we're saying it's a weak or small amount of signal, you probably say, well, all right, you can expect having issues with that, and you'll be quite correct. And on your screen, third bullet point, an exam question, such HF scatter transmissions are usually characterized as having fluttering sound or wavering sound. That's just the nature of it being pretty weak, coming and going slightly, because it's scatter propagation, as we say, trying to be go by the skin of the teeth here, actually communicating that way. Just a little bit of that signal is coming back there, just sufficient to be able to be heard, and you can communicate, but the signal is wavering or fluttering. Now, there's another thing about it. Apart from it being wavering or fluttering, it can also be distorted. Why? Because if you notice here, you'll see that the signal actually can take multiple parts. It can scatter one way like this, and it can also scatter also like this. When it scatters twice, that signal is reaching here through different paths. This is path 1, it's reaching via path 2 as well, and it's reaching at slightly different times. And what that causes, that sort of interference, constructive or destructive interference, can cause the signal to be distorted. And that's the last bullet point, exam question. Such signals often sound distorted as energy is scattered into the skip zone through several different radio wave paths. So hopefully this diagram illustrates these bullet points, and hopefully we have explained it sufficiently for us to understand what is scatter propagation. Although we would not normally be able to communicate with someone in the skip zone or the dead zone, scatter propagation, or backscatter, allows us to communicate to some extent. Right, so yet another technique, we learned about this the last time. It's called NVIS, NVIS. What is NVIS? We said it's near vertical incidence sky wave. That's another way we can drop our signal short in an area that we would not normally be able to. In other words, the ground wave wouldn't reach and the sky wave wouldn't reach, so we could try using NVIS, right? So we're trying to shoot the signal sort of almost straight up, so that it bounces or reflects or refracts and drops short, as opposed to a low angle of radiation where it will actually go all the way across the other part of the earth. You're trying to communicate here, maybe in the skip zone. So this is another way that you can cause your amateur radio HF signal to drop short. We discussed this in the last class in detail, and it's called NVIS. So a couple more diagrams to illustrate that here. Sometimes we're trying to drop our signals. The radio signal cannot go via this ground wave. It cannot go via the usual sky wave, but we can use NVIS and drop it short and probably get into nooks and crannies or valleys. All right, and we did say that NVIS is good for certain parts of the radio spectrum, above which it will not usually work. So we just have here, a definition about NVIS, and hopefully this table here will help us understand what this definition says. So it says, NVIS, or near vertical incidence skywave propagation, allows for short distance MF, medium frequency, or HF, high frequency propagation using high elevation angles. So high elevation angles of radiation to drop short. But we say MF or HF. So we have illustrated here what could be considered MF, medium frequency. So we have the meter band and we also have the frequency range. Again, we have that trusty table at the end of the slide deck. So you'll see MF and HF and VHF and UHF and so on. But we have just excerpted that here so that when we talk about it, we have a good reference. So, oh, okay, that's MF frequencies, or the 160 meter band. Oh, that's HF frequency. So we know the frequencies that we are likely to get through with NVIS operation. All right. Okay, so Arthur is asking, is the boundary of the ionosphere as straight and smooth as shown in the diagram? No, it certainly is not. Right, so excellent question there, Arthur. It's not as ideal. It's actually quite rough, if you want to call it that. It's not smooth, the boundaries are not, and especially over the surface of the earth, it can change quite rapidly as you go out further. So no, it's not as smooth as the diagrams will allude. And you probably suspected that, Arthur. Excellent question indeed. I like those types of questions. It says that students are thinking, and very lovely indeed. So yes, no, it's not as smooth. It's quite rough. All right. Okay, lovely. So let's continue a few more slides before we take our break in about the next 10 minutes. All right. So we also now come to talking a bit about radio operation practices, right? So we have essentially come to an end of radio wave propagation topic with this slide on NVIS, and we are now going on to amateur radio practices, the next major topic. So we are talking about our HF transceivers or receivers, and there are some features about them, and we're trying to show it diagrammatically here on the right hand side, as well as a screenshot of what your radio will look like. And some of these features will help us mitigate or address some of the concerns that we have described earlier as, problems or issues as hams we will encounter. We're not powerless. We have tools. We have tools in our toolkit. Our radio equipment is designed with some features that allow us to overcome some of those issues that we have been discussing as problematic throughout the course. We've been seeing, this is a problem, this is interference, this sort of issue, it's static and noise and all sorts of issues that could prevent our communication and make our life difficult. But we have tools, and we are trained amateur radio operators. We are doing a course, we are learning, and we're also going to learn about some techniques that we can use to reduce our interference. So one of those features on our radio is called the notch filter. And diagrammatically here, some radios with LCD displays, you will see it looking like this, the notch filter. And it's available on many good, whether it's Yaesu, ICOM, Kenwood, and so on. You will see it diagrammatically on the radio itself. Look at it here. You're seeing those little symbols here. Those are the filters or the notch filters. And many of them, of course, use digital signal processing. Some may actually still use physical devices. But the point is you have something called notch filters. And what it does, it actually helps reduce interference that may be present close by to the frequency you're looking to listen to. And you're getting all this static and noise. And let's see diagrammatically what we're trying to do here with our notch filter. So we have some noise here. That's this turquoise or greenish looking blob here, and this is the frequency we are trying to listen to. This is a transmission here on this frequency. We are trying to listen to this. So normally, if we have our filter here or the receive signal, we're receiving part of this noise plus our intended frequency. So what we do is we use a tuning dial or button on the radio, and we shift our notch a little bit to the left so that it's the signal, the interesting signal that we want to listen to, that ham radio operator that's talking to us, for example, we want to listen to him or her, and we shift the notch to the left so that that signal is still within the pass of that notch, but the interfering signal that was originally, this dotted line here, were originally part of what we were listening to, we kind of get rid of it by avoiding it. We're shifting this notch a little bit to the left, and we have now filtered out that noise by shifting this notch filter. This notch filter originally was in the position of this dotted line, and then we use our dial and we shifted it a little bit to the left. So all of a sudden now, by shifting, we are avoiding. And another way of looking at it is notching out that interference as well, right? So we are attenuating it. So we have the exam question here, notch filter. And of course, it's found on many HF transceivers, is used to reduce interference from the carriers in the receiver passband by blocking the interfering signal. So essentially, we are ignoring that interference by using the controls and the features of these expensive pieces of radio that we will purchase as a ham radio operator. One of those good features we're looking for, a nice notch filter. All right, so this other bullet point, I don't think it's on the exam anyway, but we're talking about this called the IF shift control. And of course, if you have a noise interference that is close by, you can use this IF shift control and slide and avoid that frequency that is causing the interference, right? However, what is on your exam is the receiver attenuator. So sometimes if a ham radio operator is close by, another radio operator is running high power or very close by, that signal, because it's so close, can overload our receive stage in our transceiver. Just because it's so powerful, it's so strong, it's nearby, and it can cause us to have issues, right? And that overload can be overcome by us implementing or switching on an attenuator in our radio called the receive attenuator, and that can help us to reduce the overload. It can prevent the overload that will occur from those incoming signals that are overbearing or strong. So that's an exam question. What is the purpose of a receive attenuator? Right? And we just have it to make it real here. When you turn on the attenuator, this is actually what may show up on your radio. This is, I guess, an ICOM radio screenshot. ATT, short for attenuator. It means the attenuator is on. And some of them have different levels of attenuation. You have level 1 attenuation, level 2 attenuation, where you can reduce the signal by more decibels. And it's shown on your screen. It can be a button, it can be a switch, it can be a knob, it can be even a touchscreen button that you just press and turn on your attenuator, the receive attenuator that reduces that incoming signal that you're listening to because it's too strong and causing issues. All right, let's continue in the line of features of our radio. And again, we have a screenshot here of a radio, the LCD, what it might look like. And this is the frequency display. This is the mode, upper sideband, the filter that's employed, the notch filter. And then we have now here NB. It's not note well, it means noise blanker. And you can adjust the level. So that's a feature on a radio. We can select the noise blanker. And what a noise blanker is that there are some noises. I mean, sometimes, for example, a car or a vehicle with the alternator can get noisy, and you could have all sorts of chipping and hums and all sorts of scratches and snap, crackle, and pops. And that can interfere with your reception of a ham radio signal that someone is talking at you, you're hearing all these noises. And you can turn on or turn off your noise blanker. Now remember, when you turn on a noise blanker, it might also reduce some of the signal that you want to actually listen to. But what it'll do, the more intelligent ones, the better ones, will focusing on what we call the noise pulses. So you'll see this is your signal here that you're trying to receive, and then you have these noises, all sorts of noises that'll be there. And the noise blanker, when you turn it on, will attenuate or reduce the receiver gain to reduce these noise pulses. It'll probably reduce your signal a bit too as well, right? But yeah, some of them switch on, switch off. Some of them may have 2-3 levels. Notice NB here that's illuminated. And some of the better radios will allow you to adjust the level of the noise blanking from 100% to 50% to 0%. So this is NB, noise blanker, and it works to reduce pulsing types of noises such as ignition noise from a car. Ignition noise meaning you have an alternator, you have maybe electronic ignition, maybe you have spark plugs. Those devices, when operating nearby your radio transmitter, maybe your transceiver is in a car, or you are near a highway or byway or roadway, or maybe someone is in the garage and that engine is on and it's causing you stress, right? So that noise can be reduced by the noise blanker because it will reduce the receiver gain when you have those pulses associated with the noise. Noise has a signature, and it can be recognized and dealt with sufficiently that will make your life a little bit easier as a ham radio operator to listen to that incoming signal, which is what your objective is. You don't want to listen to noise, you want to listen to intelligent sounds, and these features can help you. Yet another feature is called noise reduction, right? So NR. Noise reduction is another control. It uses digital signal processing, or what is called DSPs, just for your information. It uses DSP techniques to reduce other types of noises that may cause the received signal to become distorted. So you have noise reduction, which is yet another feature of many good radios. All right, let's probably take in another slide or so before we take a break. All right, so as ham radio operators, we may choose to operate Morse code. That's a mode of operation. We can do voice, what we call phone mode. We can do digital modes, as we talked about, like FT8 and RTTY and GT65, digital modes on HF. But we can also do CW or Morse code. And notice on your screen here, we have our very fancy transceiver. Right, we have the dials, we have the screens here, we have all sorts of fancy knobs on the front here. But notice we have an accessory to the right here, and we have talked about Morse code keys before. If not, you could just review the sessions. We talked about in technician class level as well. So this is a Morse code keyer, and this paddle will allow us to send the dits and the das of Morse code. So up here we have an example of Morse code, what it looks like. Right, and we may use that mode to send our messages. And the electronic keyer sometimes is a built-in feature that a radio will have that allows the automatic generation of these strings of dots, really dits, and dashes, really das, for CW or Morse code operations. So this is an exam question. What is an electronic key? It's a built-in feature that could allow automatic generation of your dits and das. Of course, we may be able to also reduce interference when we're operating Morse code. So if you remember correctly, you would probably remember that an AM signal like this has with it, you have the carrier and then you have the lower sideband and the upper sideband. So when we're sending our Morse code, we may be sending it on the upper sideband or the lower sideband. Either which way, we can actually do reverse sideband. In other words, use the other one, selecting the opposite sideband. Because what that does, it actually ever so slightly shifts the frequency. It is a technique that hams can in fact use to get rid of interference that may occur. You know, you may hear heterodyning, you may hear tones, you may hear noises, and you may just, by flipping or switching to the opposite sideband, it allows your passband to shift just enough to cause you to eliminate that interference. So this is a technique. It's also an exam question. It may be possible to reduce or eliminate interference from other signals when receiving CW or Morse code signals on a typical HF transceiver by selecting the opposite or reverse sideband. That's the exam question. And what that does, it shifts the receiver's passband up or down so that the interfering signal can no longer be heard. All right, so now that sounds like a good time to take a short 2-minute break. So please, maybe get up, take a little stretch, have a bathroom break, have some water, and we'll join you back in approximately 2 minutes time. Okay, folks, welcome back. All right, so I see David has a question here. Can we apply the principle of mesh networking to reduce the likelihood of skip zones? That's an excellent question there, David. So let me just repeat that question. Can we apply the principle of mesh networking to reduce the likelihood of skip zones? So, David, normally when we talk about mesh networking in amateur radio, we're usually talking about 2.4 gigahertz Wi-Fi. But the answer is yes. The closest I could think of that comes to mesh networking in EHF amateur radio will be what is called ALE, Automatic Link Establishment, right? So ALE would probably be one. I mean, there are a couple others as well, but ALE for amateur radio is probably the closest to what we could say might be HF mesh networking. So excellent question there, David. So it's ALE, Automatic Link Establishment. Wow, fantastic questions. Okay. All right, so let's continue. We're talking about HF operations, and of course, you know, we tend to do a lot of fancy things as amateur radio operators. So you would think, well, all right, well, we are on our frequency and we are talking with our buddy somewhere else around the world on the same frequency. We are transmitting on that frequency on HF and they are listening to that frequency and they are transmitting back to us on that same frequency and we are listening to them on that frequency. So that's all well and good and that's fine. But as hams, are we satisfied with that? No, we're not. We will do a thing called split operation where we will transmit on one frequency and receive on another frequency, and that is called operating split mode or split operations, right? So we're not satisfied to just listen and transmit on one frequency. We use two frequencies. So that is called split operations, and that's the first bullet point. It's an exam question. Operating an HF transceiver in split mode means to set different transmit, or TX for short, and receive, or RX for short, frequencies. So we transmit on one and receive on another. And of course, you know, as hams, we'll say, okay, we're listening up 5, you know. So this diagram on the right-hand side here will give you a little bit of an idea of how it works, right? And the little lingo or jargon that we use, you know, we're listening up 5. So that means 5 kilohertz separates the transmit and receive frequencies, yeah. So what a VFO is, we need to know what a VFO is because we're talking about dual VFO, variable frequency oscillator. What that really is the knob on your radio, right? When you turn that dial or the knob or the tuning knob, that's your VFO. What that is doing is, remember we talked about the receivers and the transmitters and what we need to do to receive a different frequency. We showed block diagrams. So we have oscillators, right? We need to change the frequency of the oscillator to be able to receive another frequency, for example. So that's called the variable frequency oscillator because it's our tuning dial, and we have that here. On your screen, this is a one tuning dial. This particular radio has 2 tuning dials. So that's what a VFO is. It's really the tuning dial on our radio. All right. And of course, some of the more expensive and better transceivers will have dual VFO. That means you can transmit on one frequency and listen on another. And sometimes they actually have 2 different dials and 2 different displays, or sometimes it's one display. Again, different radios, different cost structure will have different features. However, for the exam, we need to know that a dual VFO feature is commonly used to transmit on one frequency and listen on another. Another way, of course, you could think about it, you could actually listen to 2 frequencies simultaneously as well. But it's typically used for dual VFO, transmit on one and listen on the other. So that's what this diagram on the right hand side also shows here. We are transmitting on one frequency and we are listening on another frequency and vice versa. So split operations and dual VFO, variable frequency oscillator. All right, so we come to now the ALC. All right, so what is ALC? It means automatic level control. So remember when we talked about digital modes, HF modes that are running digital, we say that using a computer connected to our radio to send the signals instead of voice or phone mode where we'll have a microphone that we are talking to into the radio, and then the radio will send the signal via our feed line to the antenna and it will go into the sky. You know, we have the sky wave and the ground wave and we're communicating with someone else. But in digital modes such as FT8, RTTY, PSK31, JT65, those digital modes, the computer is doing the talking for us, right? It will generate the audio tones, and via this cable connected to the radio, it could be a USB cable, it could also be audio cables, and it will send those tones, and the radio will dutifully transmit it for us. And of course, vice versa. When we receive, the radio will receive those tones and send it to our radio, and the radio will interpret it. Sorry, the computer will interpret it via the software. So the radio sends the audio back to the computer, and that's digital mode operation. We're not speaking, we're using the computer to do the talking. So digital modes. Of course, one of the challenges with these modes, digital modes, and of course we need to know that we're using AFSK. And what is AFSK? Audio frequency shift keying. So we're using audio. So while we're not speaking, the computer is generating audio. So we can say that that mode is via AFSK, audio frequency shift keying. And when we're doing that mode, we need to be aware that we have to disable the ALC or the transceiver's ALC, because if we don't, the signal could be distorted. And this is an exam question. So we're showing here on your screen what the ALC will look like. There's a range that it will operate if it's on. And this is an exam question. If a transceiver's ALC system is not set to inactive, meaning properly, when transmitting AFSK signals, right, audio frequency shift keying signals, with the radio using single sideband or SSB, improper action of the ALC distorts the signal and can cause spurious emissions. Of course, this is a point of the exam. Of course, there are other features that could be utilized in connecting a radio to a computer to avoid this altogether. But for the exam purposes, you need to know that if the transceiver's ALC is not set inactive, meaning it's not switched off, or it is set improperly, when you transmit AFSK signals for digital modes, the radio, when you're using SSB, improper action of the ALC distorts the signal, and it can cause also spurious emission. But ALC distorts the signal is the point for the exam question. And we just have some extra information here to show you, where this distortion might occur in the signal. There's a little spurious here. Right, so you have your computer running maybe JT65 or FT8 into your transceiver to the antenna, and this is the display on your screen showing you the ALC in operation. And if you don't adjust it properly, you may have distorted signals and spurious emissions like this. Right, to be avoided as an amateur radio operator. So this is an extra slide here. I don't think this is an exam, but just to give you a little idea as well. This is a very practical point. Sometimes your radio frequency that emanates from your antenna, that leaves your antenna, that is supposed to go to the other amateur radio operator to communicate with them, it's going to the sky, the ground wave. Some of that signal could actually, if you have poor audio cables, it can probably come into the audio cable and cause distortions. It can cause issues with your radio. It could cause it to key up unnecessarily as well. Feedback, all sorts of issues you can have through what is called stray RF that is leaving either the cable or the antenna and coming and impacting your audio cable connection here. So this is just some extra information for you, something that, and there are things of course we can do, we'll see in a little while, to avoid or to mitigate against this stray RF. Okay, so we need to know what a linear amplifier is, because we're going to talk a bit about linear amplifiers, especially two-type amplifiers. So sometimes we want to improve our transmission quality. We want to improve our signal. We want to maximize our signal. So we did talk already about using our transceiver, tuning it properly on the right frequency, having the proper transmission line or feed line, having an antenna, maybe using an antenna tuner, or having an antenna that is properly tuned so that the SWR is low and we can maximize our transmit signals. But our radios, typically radios are at about 100 watts. I mean, some radios are less, QRP radios or low power radios, and some are a little higher. You can even get 150 watt radios sometimes, even higher depending. But it's typical for an HF transceiver to be 100 watts. But our license on HF, depending on the class of license you have, or the country that you're operating in, you may be able to operate as much as 1500 watts on HF, 1500 watts on certain bands. Some bands you have a power restriction. But what or how do you get a radio that is only capable of 100 watts to send 1500 watts, or what we call the legal limit, to the antenna? That is done via an amplifier. And we call those amplifiers linear amplifiers because actually we want them to be linear. We don't want them to be non-linear. They need to be linear so that our audio and our signal is dutifully reproduced properly. So we call them linear amplifiers. And we have two types. We have what we call tube amplifiers, and we also have solid state that uses semiconductors, right? So we also need to be able to adjust these things. So all these, many of them will have knobs that we have to tune and move around and switch and to be able to operate properly. So as hams, we can use amplifiers to boost our signals up to very strong levels, gain, 3 dB gain, 6 dB gain. We increase our signals. So if our radio is outputting 100 watts, we may use a 1.5 kilowatts or 1500 watt amplifier and send a higher power output to our antenna. Of course, our antenna must also be able to take that amount of power, right? So, everything is in context with each other. But as hams, we use linear amplifiers to increase our drive, to send our signal. So we may be outputting 100 watts from this radio into this amplifier, and with 100 watts in, we may be able to get maybe 600 watts or 1500 watts out to the antenna. That's the linear amplifier. So we did say that there are two types. We have the tube amplifiers or the vacuum tube amplifiers, and we have solid state. So we want to talk a bit about the vacuum tube amplifiers, and that's just because they're quite very much popular still. Tubes are not old, as we would like to say, old technology. It's still pretty much has been around for quite some time, and maybe in that sense it's old technology. But many amplifiers today that's produced, that's sold, that you can buy, will be tube-based amplifiers, and they work really, really well as well. Okay, so there's some points that we need to know for the exam in respect of our tube amplifiers. So this is our amplifier here, and it sits between our radio or transceiver and the antenna. And we may have other things like antenna tuners and SWR meters and so on. But for simplicity, we're just showing our radio or transceiver, well, without a microphone, but it's a transceiver connected to the amplifier because we want to run a higher power to the antenna. And we've just had an exploded view of this meter here. So there's a meter here. It says plate current. And then there's this knob here that says plate. That is, of course, a knob, a dial that you can turn left or right. So this is an adjustment that we're making. And this is a meter. The needle position is something that we'll be interested in when we are tuning up this amplifier, right? So for the exam, we need to know that for the vacuum tube amplifier, in making the correct adjustment for the load or coupling control of a vacuum tube RF power amplifier, it involves ensuring that the desired or the maximum power output without exceeding the maximum allowable plate current. So we want to drive this amplifier to what it's capable of doing. So let's say it's a 600 watt or 1500 watt. In this case, we want to drive it to 1500 watts. But we need to make sure that we do that 1500 watts without exceeding the maximum plate current. And that plate current, if you remember when we did vacuum tubes, we had a plate current. We do not want to exceed it because we could actually cause things to overheat. We can destroy our tubes if we apply a current that is too high for that particular tube. So we need to monitor it. So that's what this point here is about. We need to adjust this plate current using this knob to maximize the RF power output of, let's say, 1500 watts or whatever the maximum is or whatever the desired amount is, but without exceeding the plate current. And that's why we have this meter here to show us the plate current, and we have this adjusting knob to adjust the plate current. Exam question. All right, so also another exam question for vacuum tube RF power amplifiers such as this one. The reading on the plate current meter that indicates the correct adjustment of the tune control is given by a pronounced dip. What that means is, how do you know that you have the correct plate current adjustment? So as you tune this plate current, what you will see is that this needle here will be going up, going up, going up. And as it goes up, you'll see it dips back down and goes back up at a point. So the point at which you see that little dip is the correct adjustment. So that's what this bullet point means here. When you are adjusting the plate current using this knob and you're monitoring the plate current using this needle, as it goes up, just as it reaches a peak here, it will dip down a little bit and come back up. That dip or that pronounced dip is the point or the correct adjustment, right? So exam question. All right, so a couple other bullet points that we need to know for the exam in respect of linear amplifiers. One is that the ALC should be used with an RF power amplifier to reduce distortion and prevent excessive drive. What does that mean? Let's break that down a little bit. So we have our transceiver here that's connected to our amplifier. Our amplifier is connected to the antenna. But we also have another signal here called the ALC, automatic level control. And we want to make sure that we interface our radio to the amplifier using also, apart from the RF cable that connects the radio to the amplifier, we want to connect the ALC connector as well. Because what that ALC will do, it will help in avoiding that we have too much drive to distort our signal. So that's why we have this first bullet point, that the ALC should be used with an RF amplifier because it reduces distortion and it prevents excessive drive. So connecting the ALC cable, if there's such a cable between the radio and the antenna, is important to avoid distortion. We could also note here, this is just for your information, that if you have excessive drive power, that means the radio is driving too hard, you can destroy solid state amplifiers and it could lead to permanent damage to the amplifier. So if you drive it too much, you could mash it up, right? So just be aware of that. You don't want to, these things are expensive. And you don't want to, that's why you're trained, that's why you're receiving all of this information. But when you get into practice, caution, you want to read the manual and you want to go back to your notes that you've been trained on. You don't want to drive excessively. You don't want to damage your equipment that or if you're using someone else's own, you don't want to damage it, right? If you're a club station, for example, you don't want to go there and then you're driving and then you mash it up, right? That's like very expensive. So an exam question, however, is in relation to a circuit that makes sure that it's a sort of make or break, that when you transmit your signal from your radio, before that transmitter engages, you want to make sure that the antenna is engaged to the amplifier, right? So a time delay is sometimes included in a transmitter keying line or circuit to allow time for the transmit-receive changeover or the antenna switch operations to complete properly before RF amplifier output is allowed. What that means, and this is an exam question, what that means, remember, a radio is either receiving or transmitting, and the amplifier is either allowing the incoming signal to come for you to receive, or it's amplifying the outgoing signal. So imagine you are receiving. Then there's a relay inside of here that allows you to switch to the relay signal. You're listening from the antenna signal that's coming in via the amplifier to your radio. But if you key your transmitter, you want to transmit. If this amplifier starts to transmit before it switches from the receive to the transmit, you can have a problem, right? So there's a little delay, and sometimes you hear it click. You'll hear a little relay clicking. That's the little delay. You need to be aware there's a little delay, not a very long delay, but that's why also when we're operating radios, we don't start to speak as soon as we key the microphone. We need to be aware of those little delays inherent in signaling, that we take that into account. So we take a little breath before we actually start to speak, or we use a little precursor. And so that way our first syllables of our message will not be truncated because we didn't know that. So that's again why we've been trained to know about these delays, so that when we cue our microphone, we give a chance for the signal to engage, and that switching the antenna switch from the receive to the transmit position is made. Just those that short period, we need to allow for it. So this is an exam question. Right, so we did talk about an antenna tuners being important. We say hams are match makers. We're always trying to, match 50 ohms. We're trying to get our SWR to 1-to-1, the ideal. And we're trying to match the transmission line to that of the antenna feed point as well as that of the output transmitter. Right, so we will employ the antenna tuner. We came across an antenna tuner before, so we're showing a different type here. Sometimes the antenna tuner may be called an antenna coupler, and we are using it to match the impedance, right? So output impedance, so that it will be 50 ohms, right? And of course, an exam question now, the purpose of an antenna tuner is to increase power transfer from the transmitter to the feed line, because if we have a poor SWR, we will actually be reducing the transfer of that power, right? Remember we said, when it's a lossy line too and you have a high SWR, you're reducing. Why are you wasting all of that power? So you'll use the antenna tuner that will also help you to have maximum transfer from your transmitter stages to your antenna. And this is an exam question, this second bullet point. All right, a couple more slides. Right, so we now come to test equipment. As a ham, you will find yourself sometimes needing to make measurements. You need sometimes to make sure the voltages are correct. You may want to see what current is flowing. Remember, we talked quite a bit about that in the technician level, and we also talked a bit about it already in the general class level. Things like voltages and currents and resistance measured in ohms. So a multimeter, which actually allows you to measure multiple types of values such as voltage, current, resistance, and so on, is a piece of test equipment. And amateur radio operators will use it to conduct electrical measurements of the types that we have been discussing throughout the entire course. And there are two types, two main types. One is the analog type of multimeter, and the other one is the digital type of multimeter. So the analog type is this on your screen here. Notice it has a needle, hence an analog. Then the digital type of multimeter, it has digital display like this. You notice the digits. So this is a digital multimeter versus the analog multimeter. Now each has its purpose, right? And when we're connecting it in a circuit, we need to know how to connect it as well. If this is a resistor, we measure across the resistor. If we want to connect it in line to measure current, we measure it in line. If we want to measure voltages, we measure it across. So we need to know how to connect it. But we have analog and digital, and each has its purpose. Remember when we were looking at the meter on the amplifier, we said, look, you're just looking for that needle to go up, and then make a little dip and come back up. That's a lot harder to see on a digital multimeter when things go down briefly and come back up. But visually, an analog multimeter with a needle, you will see that dip visually, right? You have no choice but to see it. You may miss it on a digital multimeter. So that's one of the pros of an analog. It may be preferred when adjusting circuits for maximum or minimum values, right? So that's an exam question. Also, digital multimeters tend to have a higher precision, or it's better for most purposes, right? And if we're using it to measure voltages, and when we measure voltage on a multimeter, we'll say that that's a voltmeter. And voltmeters, the voltmeter usage in digital multimeter is that the property versus an analog multimeter is that the input resistance of digital multimeters tend to be higher. And because of that, remember we are trying to measure this resistance or maybe the voltage across here. Remember, the multimeter itself also has electronics in it, and it could present a load across here, so your measurement may not be super accurate. So the higher the resistance that this multimeter presents when you put it in circuit, the better or more accurate your measurement is. And the point here, and this last bullet point, tells you that the digital multimeter has a higher input resistance, and therefore that decreases the loading on circuits being measured. So in some ways, these digital multimeters are better because it has less of an impact on the thing that it is measuring. Exam question, this last bullet point. So we come to now a super fancy piece of test equipment, and of course, if as a ham you can get this as part of your arsenal of tools, you'll be good to go, It's called an oscilloscope, and this is an example of what an oscilloscope, or sometimes just simply called a scope, what it looks like, right? Very fanciful looking gadget. And you have the newer ones with these lovely LCD displays. The older ones would have had the phosphor type CRT displays, but these are really, really nice. And they're not as expensive as they used to be, right? And you can get pretty good quality ones, reasonable quality compared to long ago, and they're all super expensive. But what is an oscilloscope? So an oscilloscope is a piece of test equipment. It is used or can be used by hams or amateur radio operators, and it allows complex waveforms to be observed, right? Complex waveforms, right? So remember, multimeter, essentially you're seeing a voltage high or low, is going, increasing, you're measuring it and so on. But with the oscilloscope, you're actually slicing and dicing on a time scale or frequency scale. Well, time scale really for the oscilloscope. If it's a frequency scale, well, then that will be called a spectrum analyzer. But oscilloscope, you can monitor that signal over a period of time, and you can see it visually like this, whether it's DC or AC. You see a sinusoidal wave, it's a square wave, a triangle wave, a sawtooth wave. You can see what the signal looks like, and you can measure it because There are also values here that are shown. You can measure it along the wave. You can actually see what the wave looks like, as opposed to this will just show you the value of a wave at any given point in time. This will actually show you what it looks like. And you can do that. And for the exam, we need to know that it employs horizontal and vertical channel amplifiers, right? So that's why you have the x-axis and the y-axis as well. Y-axis, x-axis. And you are able to show on the coordinates the values here at any given point in time. So for the exam, it shows complex waveforms. It also uses, or it measures, by employing horizontal and vertical channel amplifiers. Horizontal and vertical to be able to display it like this. Right? Exam question. So as a ham, if you're doing Morse code, you can actually use it to monitor your signal and see what your keying signal looks like on the oscilloscope, right? So hams can use it, but check your keying waveform of a CW transmitter, and this is what it might look like. And if you see it looks a bit distorted other than what it should look like, you can adjust your radio. Maybe it's distorting, maybe these issues that we mentioned earlier, you go back and adjust some of those parameters until you get a proper looking CW signal. All right, so another exam question. If you're going to use a scope like this to measure your RF output from your transceiver, you do not connect it directly to your RF output. You will destroy your oscilloscope. Oscilloscopes are very sensitive. These terminals here, these BNC connectors as they're called, they have a limit to the input in terms of the voltage, right? And there's actually a warning here that tells you that. But if you go and connect your radio, your transceiver, directly to your oscilloscope, or in the case if it's a spectrum analyzer, and it'll tell you how much power it can take. And oscilloscopes can take usually very, very, very low signals. And transmitters such as your radio, your transceivers output high power. Even a low power transmitter is still high compared to what an oscilloscope could take. Even a QRP that will do maybe 5 watts or 10 watts or whatever low power versus even the high power transmitters, 100 watts. All of those will destroy an oscilloscope unless you take some action to attenuate or reduce the signal that is leaving your radio before you measure it. And this is an exam question. You need to attenuate that RF output before you connect it to the instrument. And the attenuated RF output of the transmitter is the signal source that is connected to the vertical input of the oscilloscope when checking the RF envelope pattern of a transmitted signal. So what it is saying here is we can use an oscilloscope to measure the output from our transceiver, but we want to sample it and we want to reduce it significantly. So we attenuate it using an attenuator. So we need to know this to avoid destroying our equipment and also to be able to pass our exams, because this is an exam question. And a couple more slides before we complete and before we go to our question pool review. So another piece of test equipment that we need to be aware of course, we would have looked at this before a little bit, SWR meters and so on. We would have dealt with antenna analyzers, but this is another set of exams and we have to deal with this here. So antenna analyzer, on your right hand side, we have what a good one looks like. We can connect our antenna via the cable to it. So this is the antenna analyzer, and to make it real, we show an example of what we might do. So this is our antenna here, and then we have our little patch cable that connects to the antenna analyzer. Notice we don't have any radio. There's no transceiver. The antenna analyzer has a built-in transceiver or transmitter inside. Well, yeah. So you can, in fact, just connect your antenna analyzer directly to the antenna. And when you do so, you're able to take measurements. So an antenna analyzer is an instrument that is used by ham radio operators to measure properties of antennas and feed lines. We do it by connecting the feed line and connecting the antenna to the antenna analyzer like so. We can also measure SWR, standing wave ratio, by just using this. Notice we have SWR measurement here, 1.4 to 1. That's what it's meaning here. So we have resistance and reactance and the frequency. So remember, SWR is at a particular frequency. So we can use these dials here and change the frequency display here to the particular frequency, and we'll find out what is the SWR on this antenna for this particular frequency. That's why we can use it instead of our transceiver to tune or determine how good our antenna is matched. Remember, hams are matchmakers. We are trying to match our antenna and the frequency that it's resonant on to that what we wish to operate on our radio or transceiver. So in order to measure SWR, or standing wave ratio, the antenna and feed line must be connected to the antenna analyzer. Now, an exam question again, the impedance of a coaxial cable can also be determined by using an antenna analyzer. So you have the coaxial cable, you connect it, and you can measure impedance of that coaxial cable. So that's an exam question. What can you measure also with an antenna analyzer? You can measure the impedance of coaxial cable by connecting it, coaxial cable, to the connector on this antenna analyzer right here. Now, there's something we need to be aware of with respect to antenna analyzers. If we have our antenna analyzer, we have an antenna and we're trying to determine what's the resonant frequency, or we have our coaxial cable and we're trying to determine the characteristic impedance of it, and we have a ham radio operator that's operating nearby and transmitting, it can affect the readings of our antenna analyzer. So I don't want to ask that ham to stop transmitting, or ask for a little, pause, please. Could you give us just a couple of minutes to do some test measurements, because the signal will affect us. Would you please, please help us out? Or maybe it's our station. So we need to know we should shut off the transmitters, because those strong signals can impact our readings here. And that's the last bullet point. It's an exam question. Strong signals from nearby transmitters can affect the accuracy of measurements when making measurements on an antenna system using an antenna analyzer. Okay, a couple more slides before we complete. So we again previously did discuss the directional watt meter. It can be used to measure SWR, and this is how we do it. We have our transceiver, we have a patch cord, we have our directional watt meter, we have our transmission line going to the antenna. And connected like this, we have an exploded view here, so you can see it a little better. And this directional watt meter can also be used to measure standing wave ratio, or SWR. What you do is you read the reverse power, you read the forward power, and that ratio will tell you the SWR. So this knob here, you turn it to the left or to the right, and you'll be able to read the power going in one direction and the power reflected in the other direction. And it's a directional watt meter. It allows you to measure power, yes, but it also allows you, by virtue of doing reverse power measurement and forward power measurement, to be able to determine SWR. Remember we said that's what SWR is? Okay. So this is an extra slide. It's not an exam. It's called a field strength meter, so you can read this up on your own time. Right, what is on our exam is the two-tone test. What is the two-tone test? So we have here our software that's connected to our radio, and we have a dummy load. It's not an antenna, and we take a sample of that signal, and we have our oscilloscope here. So remember, we showed a very modern oscilloscope. This is a bit older oscilloscope using CRT tube, but it's the same concept. You have the horizontal and vertical, and you can see a wave pattern or waveform. So the two-tone test, which we need to know for the exam, is used to analyze a transmitter's performance to determine if its operation is perfectly linear. Right? So linearity of amplifiers are important. Right? So a transmitter has an amplifier, and we want to know if it's perfectly linear by looking at the waveform. And we use a two-tone test. And how we do the two-tone test? We have a piece of software here that's running on a computer, fed into the audio input of the receiver. So we're not using our voice to do the two-tone test. We're using a software generated, or some instrument that's generating those two tones, clean signal, audio level into the receiver, into the transmitter or your transceiver. Of course, when we're connecting our oscilloscope, we need to make sure it's attenuated, and that's why we're using a dummy load here, and we're just tapping off a small bit of signal to measure it here. So we also need to know what the two-tone test comprises of. This is software here that's actually going to generate it here for us, but we need to know that the two-tone test talks about two tones, and it's two non-harmonically related audio signals. Remember what harmonics are? It's a multiple of one signal. So if you have a signal, a harmonic, you have the third harmonic, fifth harmonic, fourth harmonic, seventh harmonic. It's a multiple of the original signal. So we're saying non-harmonically related. That means that the two signals are not harmonics. One is not a harmonic of the other. Just for your extra information, it's typically 700 hertz and 1900 hertz. You don't need to know this for the exam, but we're just letting you know it's what is typical in a two-tone test. And this is what is injected into the radio. It's transmitted, and you look at the scope to see what that looks like on the output to see if your transceiver and the amplifier is linear. So this is the two-tone test. Right, so transmitter interference. So just FYI, an amateur radio station has the potential to cause interference to other services or equipment. So we have here a little bit of a spectrum, right, from 500 kilohertz all the way to 6 gigahertz, right? So you have cell phones operating here, microwave, Wi-Fi routers, we have shortwave radios, HF radios, AM, FM, cordless phones, baby monitors. We're showing the spectrum here. And as a ham, we need to be aware that our radio transmission and our equipment could potentially cause interference, sometimes what we call harmful interference to other services. So for example, if we're using our SSB voice or transceiver and we're transmitting our phone signal or voice signal on SSB, we may hear, the person might hear their speech distorted on the telephone, right? So that's an example of interference that we can cause. And just quickly, if we're using Morse code, we are transmitting Morse codes, dits and das. What can happen is someone, let's say maybe their stereo set, they may hear an on or off humming or clicking sound. So that's how interference that we might be generating might manifest itself. So a neighbor, maybe it's a person within our household, or maybe we're living in apartments and someone that's very close by, they're telling you, you know, in my stereo system, I'm hearing clickety click, or I'm hearing, you know, hum on off, hum, 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 hum. And you are transmitting. That means you're causing interference, harmful interference, and therefore we need to do something about it, either stop transmitting or find ways to mitigate, filtering and that sort of thing, right? So we can have transmitter interference. What can we do? What can we use? Are we powerless? No, certainly not. We are trained amateur radio operators. We are very discerning, and therefore we have tools at our fingertips that we could use. And one of the tools is called the bypass capacitor. So we know what capacitors are. We dealt with it in both the technician and general class levels. So we need to do this. By the way, folks, we are in fact going a little bit over time because we still have the question pool review. We appreciate the extra time. So we use a bypass capacitor, sometimes called a decoupling capacitor, and you have interference here. And notice when we use the coupling or the decoupling capacitor or the bypass capacitor, notice the interference may be significantly reduced. So that's one of the techniques that we use. So a bypass capacitor can be useful in reducing RF interference to audio frequency devices. And this is an exam question. We also have another tool at our fingertips, right? So remember we would have dealt with toroidal ferrite cores. Well, ferrite chokes, right? We dealt with it. This is what it may look like on your screen here. Sometimes you may see it already built in to devices that you buy, especially audio devices. You'll see it wrapped around, you'll see it very close to those ferrite chokes, right? Ferrite material. That's why we're learning about this, folks, so we can use it to reduce those audio common mode type currents on these devices. It will manifest itself as a hum. So placing a ferrite choke around the cable like this could reduce RF interference caused by common mode current on an audio cable. In other words, it cuts the current mode cable. If you notice here, this is actually wrapped as well, right? So these are techniques as hams we can use. Sometimes we wrap it around audio cables. Sometimes we also wrap it around RF cables, or sometimes we wrap it around power cables or DC power cables. We use it. The type of mix, the ferrite mix is also important as well, depending on the frequency you're trying to get rid of, whether it's HF or VHF, right? So as hams, we have this within our power. And this is our last technical slide. Just to mention, we have two questions that have been, we haven't encountered them yet in the course, but just to note, there are two questions that have been withdrawn from the question pool. So folks, let's quickly go across to our question pool review. All right. So let's just speed through all of these questions. We dealt with all of the theory, but let's look at what the question looks like, and we'll see the distractors as well. All right, let's start. What does the term critical angle mean as applied to radio wave propagation? It is the highest takeoff angle that will return a radio wave to Earth under specific ionospheric conditions, right? So that highest takeoff angle, that's what the critical angle is. Remember, if we exceed the critical angle, our signal will go off into space. It will not be returned to Earth. It will not be refracted. Next question, what is meant by the term critical frequency at a given incidence angle? So that is the highest frequency which is refracted back to Earth or bounced back to Earth. If we go higher than that frequency, it will not be refracted, right? So critical frequency. What is the what type of propagation allows signals to be heard in a transmitting station skip zone? So we say normally when you transmit your signal, it goes via the ground wave and it stops at a point, and it also goes via the sky wave and it's bounced or refracted and dropped several thousand kilometers away. But there's an area that's called the skip zone that there's no signal going. But we can, in fact, get some signal if there's a scatter propagation or backscatter. Really, it returned, it's a kind of weak signal, but that's scatter propagation. Why are HF scatter signals in the skip zone usually weak? Well, it is because only a small part of the signal energy is scattered into the skip zone. That's why it's usually weak. Only a small part. Also, what is a characteristic of HF scatter? So we did say that you get a wavering or fluttering sound. So signals have a fluttering sound. What makes HF scatter signals often sound distorted? Well, it's coming via different paths. So energy is scattered into the skip zone through several different paths. So that causes it to be distorted because you have constructive and destructive interference via the signal coming in via multiple pathways. All right, NVIS. What is NVIS? What is near vertical incidence skywave propagation? It is short distance for HF or MF propagation at high elevation angles. Right, so moving right along, what is the purpose of the notch filter found on many HF transceivers? Let's dissect this. What are they asking us? The purpose of what? Notch filters, okay? It is to reduce interference from carriers in the receiver passband. Notch filter, so we are notching it out. What is the purpose of using a receive attenuator? Well, we use it to prevent receiver overload from strong incoming signals. Next question. How does a noise blanker work? It works by reducing receiver gain during a noise pulse. Next question. What happens as a receiver's noise reduction control level is increased? Let's repeat that. What happens when a receiver's noise reduction control level is increased? In other words, we are turning up the level of noise reduction. Well, the effect of that is our received signals may become distorted. All right. Next question. What is the function of an electronic keyer? So we're talking Morse code here now. Automatic generation of dots and dashes, or dits and das, for CW. And CW is Morse code. CW operation. It means continuous wave, but think of CW as Morse code. Okay. What is the benefit of using opposite, or the opposite, or reverse sideband when receiving a CW? So we say this is one way to eliminate interference. It may be possible to reduce or eliminate interference from other signals. Good. Continuing, which of the following is a common use of the dual VFO feature on a transceiver? So we're talking about the dual VFO, variable frequency oscillator, dual VFO on a transceiver. It allows us to transmit on one frequency and listen on another. Remember we said 5 up, meaning 5 kilohertz up? Yeah. Okay, why should the ALC system be inactive when transmitting AFSK signals? So we did say that the automatic level control must be, it could distort the signal, that AFSK, audio frequency shift gain signal via digital mode. ALC action can distort the signal. All right. What is the correct adjustment for the load or coupling control of a vacuum tube RF power amplifier? So we said that The answer is desired power output without exceeding maximum allowable plate current. That is the correct adjustment. You maximize your RF output, but you do not exceed the tube plate current. All right. Next question. What is the effect on plate current of the correct setting of a vacuum tube RF power amplifier tune control? Let's dissect this question. What are they asking us? What is the effect on plate current, but of what? When we have the correct setting of the tube tune control. So we're tuning the tube, right? We are using the tune dial, and we are looking at the meter. How do we know we have the correct tune value, or that knob? How we know the position is correct? We know it's correct because we will see a pronounced dip. As we turn that knob, we will see the needle dip a little bit and come back up. That point of dip is the correct setting. Why is automatic level control, or ALC, used with RF power amplifiers? So remember, we are connecting our transceiver to that RF power amplifier, and we are connecting the ALC cable between the two. Why are we using that ALC control? It is to prevent excessive drive. If we have excessive drive, we may have distortion, and we could also damage equipment, right? What is the purpose of delaying RF output after activating a transmitter's keying line to an external amplifier? All right, so let's read that question again. What is the purpose of delaying RF output? So in other words, after you start to transmit your transceiver, before the amplifier starts to transmit, there's a little delay. What's the reason for that delay? The answer is, it is to give time, or allow time, for the amplifier to switch the antenna between the transceiver and the amplifier output, okay? Or between receive and transmit. What is the purpose of an antenna tuner? So we did say hams are matchmakers, right? So we do that to increase the power transfer from the transmitter to the feed line. Antenna tuner purpose. Okay. Couple more questions, folks. We're a little bit on overtime. Thank you. What is an advantage of a digital multimeter as compared to an analog multimeter? Well, one of the advantages of digital is higher precision. Why do voltmeters have high input impedance? It is because we want to decrease the loading on circuits that are being measured, right? So that's why. When is an analog multimeter preferred to a digital multimeter? Well, we just talked about it when we were doing, tuning up our amplifier, right? When we are adjusting circuits for maximum or minimum values, we see it visually. Much harder to see on a digital scale. All right, what item of test equipment contains horizontal and vertical channel amplifiers? Let's dissect this question. What are they asking us? What item of test equipment? Is it a multimeter? Is it an antenna analyzer? It is a SWR meter? Is it an oscilloscope? That's what they're asking us. What item of test equipment? That contains a horizontal and vertical channel amplifiers. Remember, the one that has that display, the time domain, it shows the vertical and horizontal axes. So therefore, the amplifiers that take the signal in and display it is part of an instrument called an oscilloscope. Which of the following is an advantage of an oscilloscope versus a digital voltmeter? It allows us, that's the oscilloscope, it allows us to see complex waveforms. So complex waveforms can be measured. Which of the following is the best instrument to use for checking the keying waveform of a CW transmitter? Again, that trusty oscilloscope. Great piece of equipment, or great piece of test equipment if you can get it. What signal source is connected to the vertical input of an oscilloscope when checking the RF envelope pattern of a transmitted signal? Let's dissect this question. We are using an oscilloscope, and they want to know what signal do we connect to the vertical input when we are checking what? An RF envelope. In other words, our ham radio signal output. Well, it's an attenuated RF output of the transmitter that we are connecting. Why attenuated? Because if we send a full unattenuated signal, we will destroy our oscilloscope very easily and cry. Okay, which of the following must be connected to an antenna analyzer when it is being used for SWR measurements? Let's dissect this question. What test equipment are we using? We are using an antenna analyzer. And what parameter are we measuring with that antenna analyzer? It's standing wave ratio, SWR. So what must you connect to the antenna analyzer to measure SWR? Well, it's the antenna and the feed line. Yeah. Next question, which of the following can be measured with an antenna analyzer? Well, of all of these things listed here, we can measure the impedance of coaxial cable. Right? What effect can strong signals from nearby transmitter have on an antenna analyzer? Well, it can affect it. The received power can interfere with our SWR readings, right? Okay, next question. Which of the following can be determined using a directional wattmeter? We said we can measure SWR, or standing wave ratio. What transmitter performance parameter does a two-tone test analyze, right? So we're dissecting this question. We are using a two-tone test, but what test does that check for, or what does it analyze? Or what transmitter performance parameter does it check for? It checks for linearity, right? Making sure that it's linear. What signals are used to conduct a two-tone test? Well, we use two non-harmonically related audio signals to conduct a two-tone test. All right, what sound is heard from an audio device experiencing RF interference from a single sideband phone transmitter? Let's dissect this question. What are they asking us? What sound is heard when there's an RF interference from a SSB or single sideband phone transmitter, but on an audio device, let's say like a phone, telephone, or maybe a stereo system? Well, the sound that you hear from SSB phone transmission is distorted speech. Okay. Similar related question. What sound is heard from an audio device experiencing RF interference, but this time not from an SSB or single sideband voice or phone transmission, but from a CW or Morse code signal or transmitter? What you hear is on and off humming or clicking. Right. Next question. Which of the following might be useful in reducing RF interference to audio frequency circuits? Let's dissect this question. What are they asking us? Which of the following, and they mean devices or component, might be useful to reduce what? RF interference. But RF interference to what? To audio frequency circuits. So, you know, like a headphones, stereo, a telephone. What might be useful? Well, we show that a capacitor could be used, a bypass capacitor could be used to reduce RF interference to audio devices. Okay, so last question in the question pool. Which of the following could or would reduce RF interference caused by common mode current on an audio cable? So the key here is common mode current. So that's a ferrite core. So we place a ferrite choke on the cable. So folks, that is the we have been dealing with pages 79, and let me just share back the slideshow. Right. So we have been dealing with pages 79 to 91 of the No Nonsense Guide. And This is our trusty table that talks about MF for medium frequency, HF for high frequency, VHF very high frequency, UHF ultra high frequency, and the various amateur frequencies 1.8 to 2 megahertz, 3.5 to 4 megahertz, as well as the 160 meter band, 80 meter band, 20 meter band, 6 meter band, 2 meter band, and so on. Good chart, handy chart to help you until you have this and know this back of hand or second nature. Good reference chart. So folks, we see everyone has stuck with the extra time. We really do appreciate. We know we ran over time just to cover the material. Thank you. Everyone stayed with us. No one left. We really do appreciate that. Shows your interest. Any questions? I know we dealt with some. Any additional questions that you have, please send an email to this address. Also, you can send a WhatsApp message to this number. We have a WhatsApp channel. Feel free to join it. We also send out the meeting reminders and the links, as well as any extra information that may be relevant if you're interested. You can feel free to join this WhatsApp channel. It's an open channel. You can also share it with anyone who would be interested in this type of information. So folks, our next session is scheduled for next week, Friday, 26th of January at 8:30 p.m. So thank you very much, everyone. Take good care. Be safe.